Okay, good evening, everyone. Yeah, this is the open session for week 10. So, so how was, yeah, any doubts regarding week 10? How did you find the lectures? Did you go through the lectures? Uh, are you finding certain things difficult? Yeah, does anyone
Yes,
want?
sir. Sir, I am facing some issues in like understanding the finite state automaton and its graph, like how to represent and how to match the prefix.
Yes, yes. All right. We will talk about that. Sure.
Sir, I'm having some troubles in like suffix tries, like how some properties of suffix tries, like how can they count number of substrings, like by just counting the leaf nodes and all that.
All right. All right. Sure. So one is suffix tries. Yeah, then you said the automata. All right.
Especially sir, graphical part in the automata.
Hmm.
Yeah.
Got it. Yeah. Yeah. Any other doubts? Have you all watched the lectures? At least some of it. None of them. Any responses?
Up to
Right.
Knuth-Morris-Pratt we have watched. Some of us watched.
Okay, the KMP one, right? Yeah,
Yeah.
Knuth-Morris-Pratt. Okay. All right. All right. Okay.
Not
Yeah,
that
I
we
could.
fully got it, but
Yeah, yeah. I think along with the automata, I will talk about the Knuth-Morris-Pratt also. Yeah, so all right. So I think we have enough things to discuss. Let's get into week 10. I'll just start sharing my screen. All right. Okay, so in week 10, the focus was on string matching, right? So we have a string or we have text and we have a pattern. And the objective is to see how many occurrences or where all are these patterns occurring in my text, right? And there are several algorithms which do that. And I'm sure all of you are familiar with the applications of this, right? Anything which you want to search today, uh, in your files or almost everywhere, right? String matching is such an uh, important functionality of any software, of most software. Uh, so this week we were looking at some of those algorithms. So, uh, okay. So let me just, yeah, yeah, just to motivate with an example, right? A simple example of, right? So that you know what it is. So let's say you have a string like A, B, A, B, uh, A, B, A, B, A, C, A, B, right? So let's say this is my text, right? Whatever that is. And then I want to match, let's say, a pattern, which is A, B, A, B, A, C, right? So if this is the text, I want to see where all this pattern occurs in my text, right? That is the objective. And of course, there is the brute force approach of looking at, this is of length 1, 2, 3, 4, 5, 6. So looking at the first six letters, 1, 2, 3, 4, 5, 6, see if it matches. Like compare A with A, B with B, A with A, B with B, A with A, and B with C, right? And we realize that it doesn't match. Shift by one, the next, and so on, right? And this is the brute force approach, where what do we do? Yeah, just write it here. A, B, A, B, A, B, A, B, A, A, C, A, B. And you have a pattern, which is, let's say I want to match A, B, A, B, A, C, right? And what it does is, yeah, so T, this is my T, which is my text. And I just iterate through each and every letter in my text, right? And it is, yeah, it is not length T, but length of T is this entire thing. But I need not go till the very end because I just need to check till wherever my pattern P is there, right? So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. I actually need to check only till here. That's why I'm subtracting length P and adding one, right? And what we just said, right? I will look at, I'll initialize J to 0, right? And this is my I counter, which will go through T. And I will always check if Ti plus J, right? Uh, yeah, and J will iterate through the length of P, right? So J will take value 0, 1, 2, 3, 4, 5. And each time I will check if the Jth, the pattern J, Pj, right? And the text, which is actually I plus J, right? If it's matching. So for example, in this case, I is 0, J is 0, right? And my J is here. I check if both match. Yes, I increment J, right? I increment J, J comes here. Now J is 1 and I plus J is actually this. I check these two, it matches. Then again, I increment J equal to 2. I come here, matches, it matches, it matches. And now finally I reach J 0, 1, 2, 3, 4, 5, right? J is 5, I is still 0. And I see that both do not match. And when it doesn't match, match becomes false. And when match becomes false, right, it will exit out of this loop and it will check, right? If it is matched, then it will append that ith entry, which denotes that from starting from here, okay, I can get this pattern P if I start from here. And in this case, we see that it doesn't happen. Then what do we do? I increments to I plus 1. So now I comes here and I continue the same process all over again. Any doubts in this? Right, this is a simple naive algorithm, right? And but the issue with this is, yeah, the issue with this is, yeah, the worst case is n into m, right? This is running, n is the length of the text, right? And see, for example, if my string is all A's and I have a pattern which has A's ending and ends with B, then each time I have to go through, for each n, I have to go through this pattern. This while loop runs m times, right? So m into n, which is nm, which is the complexity, right? And what the next algorithm, which tries to do it in a better way, is to start, instead of starting from here, right, from the start, we start from the mth position of the pattern, right? We go backwards instead of forwards, right? And that is the Boyer-Moore algorithm, right? So any doubts in the brute force, the naive approach? All right.
Sir, how starting from the end a smarter approach?
Yeah. I'm explaining that right. Yeah. All right. Yeah. Okay. So what I mean by that is, in this Boyer-Moore algorithm, yeah, what we do is we, yeah. So remember earlier what we used to do was we used to uh, compare B and B, then A with, since it's same, then we increment by one and check the next two, right? But in a way, you can speed it up if you go from the right. So what this algorithm tells is, so in this example, if you see, you check the rightmost, I mean the last element, sorry, the last letter in the pattern K, right? You check it with the text. If it doesn't match, right? And in this case, you can see that none of these letters are actually there in my pattern, right? What we can do is that we can directly jump those many places. Okay. So we can directly jump those many places and go to the next part. Again, we see here that K and A do not match. So we can again jump and go there. Okay. So let's take an example. Maybe let's take the same example.
Sir, but didn't we miss the possibilities in the middle?
Sorry.
Okay, I didn't understand, sir. How can we jump? For example, if the pattern was found from 2 to 5, say, in that case, if we had made the jump, wouldn't that be a mistake?
The thing is, like if the last letter is not matching, and the initial, like if the initial part matches and the last is not matched, so the overall pattern will not be matched, right?
Yeah, but what if the K had matched with not the A but the N? That's also possible, no?
Yes,
But
yes.
if you want to match K with N, then there should be at least three letters before N, right? Then only we'll be able to form the four-letter match.
Yeah, but here we have 3 letters before N, no?
Which N?
I'm talking about the second N.
You're talking about this N?
Yes, yes.
Okay.
So that basically the algorithm will skip to that position, right? Because it is not A and K is not matching though. So it will start from matching B with N, the next N.
Yeah, right. We are not skipping the N. We'll start from N, right?
Yeah. We won't skip this N. Yeah. So we will, next time you see, we will compare K with A, M with L, A with U, sorry, A with K, and we'll realize that it's not matching, right? And in this case, we are lucky in a way that none of the things ahead of it are actually there in the pattern.
Right, if it were there is my question.
Yeah. So we'll come to that. So that's a good observation, right? So in this case, we were lucky, like uh, whatever is there in my pattern, like we got the first mismatch, and luckily the letters next to it were not there in my pattern, right?
So, sir, like we are first we'll match the last letter, and if letters match, then we'll move backward and match all the words, right? All the letters.
Yes,
So
yes, yes.
this way we'll cover all the letters. If the first letter is not matched, then there is no chance that the pattern will be matched. So that is why we'll skip the letters and move forward.
Yes, yes. Yeah, yeah. That's true. But okay, let me just
Yeah. So I think just the key point here is if A doesn't match with K, we are checking if A has any match at all in this whole bulk. And if A is not there in bulk at all, then the entire thing gets shifted to the next.
yeah,
Yeah,
yes.
exactly.
Yeah, yeah. So in but sorry, whose question was it? But if A was there in somewhere in bulk, right? Then what should we do? That is your question, no? Whose was it?
Yeah,
Sorry.
yeah.
Correct, correct. Yeah, we'll come to that. Okay. Okay, good. So let's see if that example is there.
Then we'll shift that to pattern bulk in such a way that both the A's are aligned.
Exactly. So what we should do, so let's take this example, no? Haystack width, okay? And so let's take this as, okay, let's take haystack width and stick, okay? Haystack width, yeah. So let's take a stack width and stick, right? So STICK, right? So according to the new algorithm, what we are saying is we will compare K with T, right? And when we realize that it's not matching, right? Now, what should we do? We should look, yes,
We should
yeah,
look
Vedant.
if there is any occurrence of T in the pattern.
If there is an occurrence of
T in the
T in
pattern.
yes, and then
So T is here, so we'll shift this in such a way that the both the T's are aligned in.
exactly, correct. So we will try to shift, okay, we'll shift this. So okay, yeah, so then we will shift it in such a way, right? So initially, okay, let me just, initially we were here, right? STICK, and we compared these two letters. And what we realized is that they are not matching. Since they are not matching, right? But we realized that, okay, so let me make this as stick, okay? Yeah, haystack with, okay? So if this was, yeah, the other approach which we could have done was we could have directly jumped and put S here, T here, I here, C here, and K here, right? But you noticed what happened? Our pattern was sitting over here, right? And if we had just directly jumped across the entire thing, we would have missed that. So is that clear? Why we can't directly jump to the next letter? Okay, so that's the reason why we need to somehow look at, right, where if if this letter T occurs somewhere over here in the prefix of the pattern. Sorry. Right? And we realize that yes, it is there over here. So we try to somehow align this T with this T. So this becomes S and T, I, C, K. Is this clear why we did this? Any doubts in this part? All right. Okay. Okay. So good. So we came here. Now again we follow that approach, right? We look at the last. Yeah, we look at the pattern from the right. We see it's matching, 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 matching. And we reach the end of the pattern and we realize that it's matching. And when it matches, what should we do?
Shift by 1.
Okay, why not shift by, why can't I make it, why can't I move it here, like here?
Because we have to start it again. We don't know, like we can miss some cases if we shift it completely.
Exactly. The same issue, right? It could have very well been that stick could have been somewhere over here, for example, right? So we shifted just by 1. All right, and we continue this till we reach the end of the text. Is this clear? Any doubts? All right, so let's just quickly.
Is it possible that there are 2 characters that are matching? No, I'm just trying to imagine a situation where there are 2 characters matching. So in this case, like for example, the last character was present in yeah. So this T was present somewhere else, right?
Over here, right? Here.
So if you write stick, I mean the pattern is stick, right? Pattern is
right,
stick.
right. Yes.
Okay.
Yeah.
Now in case. Yeah, so S is also matching, but we directly align with T only because T is the latest match.
Right, right. Yeah.
Okay, and we don't have to worry about cross matches. Like I can have an A later or something like that.
Yes. Suppose if this was STI, TK. Okay, for example.
Right.
If it was instead of stick, it was STITK, then now we have 2 T's in our pattern, right?
Correct.
Where should I shift my pattern? So 2 possibilities are there. Either I can make it, I can shift the T over here, and this is ITS. This is one possibility. Or I can shift it to this, right? In that case, it is STITK.
Yeah, so it'll be the first one, is it? Because that will be the earliest comparison we can do.
No, the second T, na?
Sorry, so let's say this is case 1 and this is case 2.
So I meant case 1.
Yeah, case 1.
Right? Why case 1? Why not case 2?
Because we
have to
could
check
have a match before that, right? We could have a match at the first 3 characters also, which we would be
exactly
missing.
Right. So it could have very well been that we could have had a match here, right? And if we don't do that, then we could have missed that, right? So yeah, so this brings us to an important point, right? So if there are uh, repeated things or repeated letters in the pattern, choose the pattern which comes last in a way, right? Right? Is that clear?
Yeah.
Yes, sir.
Okay, good. And
But is
that's
there a
exactly
possibility of moving backwards, sir? Like, I mean, okay, we are at the beginning, but somewhere in the middle, is it possible that we could have a match and therefore the words are moved backwards? Is
the
that a
text,
possibility?
the
Yeah, the
text or the
pattern.
pattern.
The pattern.
Yeah,
So
yeah,
right now
yeah.
we are moving the pattern forwards, right? So we are
Yeah,
moving
right.
from left to right.
Hmm.
But is there a match possible and therefore we have to move backward from right to left? And then in that case, you will have to, you will keep going backwards. I mean, I don't know.
Yeah, that is why we are using this max thing in the code.
Yeah, 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 yeah. That's a good point. Yeah, we'll come to that. Right? That's a good point.
Sure, sure.
All right, all right. Oops, sorry. Okay, so let's quickly look at the code, right? And we'll see all these cases coming up in the code, right? So, right. So one thing which we have sort of hand waved is, how do we actually match? So if it was stick only, right? STICK. How do we actually realize that we have to shift this pattern and align it with this T, right? So that's the reason why we compute something known as this dictionary, which is called last, right? So what last does is it tells me the position of a character in the pattern.
Rightmost occurrence of that character.
Yeah. So for example, if we had taken STIPK and try to compute last, right? So last is a dictionary, right? Which iterates over the pattern, and last of P of I. So last of S is I, which is 0. Last of T is 1. Last of I is 2. Now last of T, okay, it was 1, but as you know, in a dictionary, we can have only one key. So this becomes 3 and K is 4, right? So this actually helps us, you know, look at you can say the latest or the rightmost occurrence of a particular, uh, of a particular character. All right. Okay. So this is my last dictionary. Okay. And now let's see how this works. Okay. So let's look at the code. So we see that again, it is iterating through. I is going from the 0th element to, so I is going from here, from left to right, right? And like the previous algorithm, we have a match which is initially set to true, and whenever we see that it's not matching, it becomes false, right? And if it is matching, we have something called as a pause list, which takes the positions where it is matching, and we append whatever my I is there, right? That is getting appended. Otherwise, we do something, right? This is the part which we need to look at. And if, we look at that. But another important thing to note is that we are, J is initially, in the previous case, J was starting from 0, right? J was starting from 0. But here we see that J starts from the length of P minus 1, right? So let me take it as stick on STICK. So this is 0, 1, 2, 3, 4. j starts from 4, right? And it continues till j greater than or equal to 0. So this while is going till here, right? And if it is matched, right? So it will continue till we get a till matched is true, right? So what happens here? We see that for now it compares t of I plus j. Remember, j is 4, I is 0. So this is 0, 1, 2, 3, 4. So t is compared with k. Immediately we see that it is not matched. So matched is equal to false, and j decrements, right? So j becomes 3. And it's not, and matched, in the next iteration, matched becomes false. We come out of the while loop and we check if it is matched or not. And in this case, we see that it's not matched. Okay. All right. Now, what happens is, remember we decremented j, right? And actually, we got an unmatch here itself, a mismatch here itself. So that's the reason why we need to increment it again, right? The reason being, we had decremented j. We realized matched is false. Then we decremented j, and only after that we checked if matched is true or not, right? So there is an extra decrement here. That's why we are incrementing it here. So this tells me that my fourth position in the pattern doesn't match with the text. Okay, right. And now this condition, right? If t I plus j, which is this is I plus j. So if this, we are checking now whether this t is there in our last of keys. Okay, so remember, this is the reason why we need to know by how much we need to shift, right? Let's say if it was not there at all. So what does that mean? Let's say this was false. So let's say this letter T was not there in my last of keys. So what does that tell me?
Shift everything out. I mean, shift the whole pattern beyond I plus j.
Right, right. So let's say it was okay. So the pattern, instead of stick, it was let's say T, right? T wasn't there anywhere. It was, let's say, A, B, C, D, E. We wanted to check if this had A, B, C, D, E, right? Oh, sorry, not E. E is already there. Yeah. So let's say the pattern was P, Q, R, M, N, something like this, right? So you would notice that P, Q, R, M, N, right? You would compute a last for that, and you would realize that T is not there in last of keys, right? It's not there at all. So that means that whatever is there in the pattern, sorry, T is not there in my pattern at all. So what does that mean? There isn't a possibility of T appearing anywhere towards the left of my pattern. And so I can just directly jump over here. That's why I can if that is not the case, I can directly jump I equal to my new position of the text from where I should start scanning will be I plus j. Oh, sorry, not here. I plus j plus 1. So I can directly start from here. Is that clear? Okay. So in this case, if you see, t, okay, so we were here, right? T of I plus j, which is the text, this letter T, is actually there in my last of t's, which tells me that T is there in the pattern somewhere, and it is T. It is actually there in position 3. Right? And since it's there in position 3, that's why I don't want to increment to this part, but somehow I want to align this T with this T, right? And how do I align that? I look at J, right? Whatever my J was, in this case it was this, and I subtract that from whatever is my last of T, right? Is that clear? So in this case, it will be J is 4, 4 minus last of Ti plus J. Ti plus J is this T, last of T is 3, 4 minus 3 equal to 1. So I will just increment I by 1. Is that clear? So so when I increment, remember I was 0, now I comes here. So this becomes S T I T K. We see that both of these are aligned. Any doubts here?
So here basically what we are doing is we are looking for the character that is not matched in T in P, wherever was its last occurrence. And by that much, we are moving the difference between where we found the mismatch and where we found the last occurrence. By that number of characters, we are moving to the right. That's what we're doing,
Yes,
right?
exactly. Yeah, yeah.
Okay.
Right. And once we come out of this, then we again go to the while loop and then we continue this, right? So remember our J was here, right? J was here. Then we compare this with I plus J. So J, yeah, now I plus J is here. This is I plus J. Then we compare. Immediately we see that there isn't a match, right? And what do? So if there is no match, we come here and we see T of I plus J, which is I. I is there in last of keys. Okay, it is in position 2, right? And what does this tell me? We have to somehow align these two. So in a way, we have to shift this by 2, right? So that's what we're doing now. J is 4, 4 minus 2, which is 2, I gets incremented by 2. So I comes here. So I gets incremented by 2. Is that clear how we got this? Okay. And then we continue this, right, till we match. So if Naveen raised his hand. Yes, Naveen. Naveen, you had a doubt? All right. Okay, so then now the next time so this now it will become STITK, right? It is shifted by 2. We come here. Okay, and we continue this until we get, so in this case, if this was CK, right, for example, so we would continue this while, and each time it is getting matched. This matched with this matched with this matched with this matched with this, and this matched with this. And our match becomes, we exit the while loop and matched is true. And my position dot append I now is here, right? This is my I, and that gets appended to the position list, which tells me that at 0, 1, 2, 3, at the third position, right, stick is present in the pattern stick is present in the text. Okay, any doubts? Any doubts in Boyer mode?
So that max that is used is again for backward push, is it? I mean, just as an example, if you could give some.
Yeah. Sure. Yeah, I forgot to mention that. Sorry. So I think let me take a good. Yeah, why don't we take yeah, so let's take a pattern like A B A, and a pattern so okay, so I don't know, let's see. Does anyone have an example of that? I don't know if this will work. Where no, this one. Yeah, so there can be a case where, okay, there can be a case where J minus last of Ti plus J becomes negative. Okay, so what does that mean? That means that J is somewhere in my pattern, right? And yeah. So let's say I've reached here somehow, right? And I've not matched it. And what can happen is the last occurrence of S can be, sorry, the last occurrence of S can be somewhere over here, ahead of this, right? The last of this can be somewhere ahead of this position. In that case, it will be negative.
Like
right?
in this haystack case, if A occurs later in stick, like for example, if it is STATK or something like that, will that happen then? Instead of STITK, if it is STATK, and you're matching from AY, you're matching AYSTA.
Okay, you are matching AYSTA with
STATK.
okay.
I think the first itself there's a mismatch. So we'll have
Yeah,
to take a case where there is a mismatch in the middle.
yeah, yeah. Yeah, there is an example. Let me just think of that. Yeah, yeah. So in the pattern, yeah. Yeah, let's take this only, na? STITK only. So we have STITK, and let's say I have reached here, okay, and I see a mismatch, okay. So uh, so if the word was, let's say, it's a mismatch, no? So yeah, so let's say it was something like A, B, C, D. No, sorry. Correct, correct.
Probably ATITK may work, or
Exactly.
ABITK or something.
So yeah, ITK is there. ITK has been matched.
AIITK may work.
Yeah, yeah. So now in this, let's say it was something like BAITK. So ITK has been matched, right? Now when we reach here, we see that it's not matching. Now I need to shift this T to an appropriate position, right? But we see that there is already a T over here, right? And last of T is actually 3, which is 0, 1, 2, 3, which is this position. But my J is 0, 1. So 1 minus 3 is actually equal to -2, right? And what it is telling me to actually do is shift I to behind, right? So I was actually here. It is actually telling me to go back here, right? But I've already done this. I've already compared AI,
Right.
right? So that's the reason why we take max, like we either increment by 1, or if j is ahead of last of t plus I plus j, then we shift to the right. Yeah. Is this clear? Anyone has a doubt in this? Why this came? All right. So although this appears that, we are skipping a lot of letters and jumping ahead, but we can take counter examples for which, this doesn't, this will again give the m into n times complexity, right? So even in the slides, you would see that Sir has taken an example of, let's take T as the string of all A's, right? And if we have a pattern which is BAAA, right? So in this case, what we are doing is we are again checking, and we check 1, 2, 3, 4. We do m comparisons each time, and we just shift by 1 each time, right? And this is again an order n into m, right? So Baremur also, even though we are trying to do this from right to left and we are shifting towards the right by more than 1, there are some cases where this is also order n into m. Okay, so any doubts in Boyer mode? Okay, then Paul had a doubt in the automata part, right? So shall I skip Rabin-Karp for now? Anyone has a doubt in Rabin-Karp?
Sir, I have just one doubt in Rabin-Karp. The pre-processing bit, which is converting text into numbers, right? Is that as simple as just saying, A is number 1 and Z is number 26? Is it as simple as that, or does it involve more logic? And because I think that part has not been covered much. So
yeah, that's a good question, Kaushik. Yeah, so yeah, it involves something more than that, right? Maybe what we can do, we'll take a quick example then, right?
So do we take the ASCII values?
Yeah, definitely. We can take the ASCII values, but as Kaushik was saying, no, it's not a simple substitution.
But still, like, we just need numbers, right? Then we mod it, so it doesn't really matter.
Okay, we mod it and then?
So like when we, actually sir told that we can mod the part we do of the rolling thing, like, and then it's not like much computationally intensive to compute after modding.
Yeah, it's not intensive to compute, but is it, I think what Kaushik is asking, is it just a, so for example, let's take A, B, C, D, E up to Z, right? So let's say my string is A, B, sorry. Let's say my pattern is XYZ. XYZ. Can I directly translate this to what is X? 24, 25, 26. Kaushik, is this your question?
Yeah, that's correct. Or I mean, whatever, whether we take ASCII or just a simple translation, but is it as simple as this, or does it involve something else?
Yeah, that's a good question. Yeah, maybe we'll just look into it. I'll just are others aware of what Rabin-Karp is, or if I don't explain that, then all of you will be lost. Does anyone want me to quickly explain what we are doing in Rabin-Karp?
Yes, sir.
Yes, sir.
Okay, I'll do that. Okay, so so just to recap, right? What did we do? We started with the brute force approach where we looked at I, then each time we are going we are incrementing I by 1 and checking if there is a match, right? With the pattern and with the text. Then we said, no, there's a better way if we go from right to left, right? We check if it is matching. If it is not, we look at the positions where there is a match and we shift it by that much to the right, right? We shift the pattern to the right? Now, Rabin-Karp proposes a different approach altogether, right? What this algorithm says is convert these strings, right, into numbers, right? So I'll take Sir's example only, right? Yeah. For this also there was an example. Okay. It's not. Yeah. So let's just take numbers from 0 to 9, if you see. So, and let's take my text as a simple one now, say A, B, C, D, E. And I want to check if the pattern BCD, BCD is there. Okay. Now, what Rabin-Karp tells is somehow convert the text and the pattern into a number. And then what you can do is perform arithmetic operations on it rather than, checking if each part is equal to the other in the text and the pattern, right? So this can be like a very simple encoding that, A is 0, B is 1, C is 2, D is 3, and so on, right? So this will reduce to 0, 1, 2, 3, 4, 5, 6, and the pattern will be, can you tell me what's the pattern?
1, 2, 3.
1, 2, 3. Good. Yes. Right. So now we have to, now these are transformed into numbers. And what we have to do is check whether, this number, yeah, somehow whether this 1, 2, 3 is there, right? And what we actually do is we take the first 3 numbers, which is 12. We check if 12 is equal to 123. No, it's not equal. Then I check 123. Is 123 equal to 123? Yes. So then, so notice this is not the string 1, 2, 3, but it is the number. So that, if this was a string, then you had to compare 1 with 1, 2 with 2, 3 with 3. But this is a single arithmetic operation of checking whether the number 1, 2, 3 is equal to the number 1, 2, 3 in the pattern. Right? So here itself, you can see that we are just doing 1, 2, 3, 4, 5 comparison. Right? We are not checking the individual digits. Right? So that is broadly what Rabin-Karp, the Rabin-Karp algorithm is saying. Right? Okay, so let's quickly look at this algorithm, right? So, yeah, so like the previous case, we have T and P. T is the text, P is the pattern. Now we have to transform this text into a number, which is num_t, and transform the pattern into a number, which is num_t. Initially, both are 0, right? And now we iterate through the numbers in the pattern. Okay. Okay. So now let's see. So what is actually happening here is we are actually translating this pattern into a number. Okay. So what is happening? Initially, both are 0. So what is num_t? Num_t is 10 into 0 plus int. Remember, this ti is a string. T is still a string of 0, 1, 2, 3, 4, 5, 6. We are translating that into a, sorry, we are converting that into an integer. So T of I, right? T of I is 0. So 10 into 0, 0 plus 0 is 0. Is that clear how we got this?
Yes, sir.
Similarly, num of p is 10 into num p, 10 into 0. plus int of p of I. Remember, p of I is this plus 1, which is equal to 1. Okay, so now it is 0 and 1. Now again, for the next I, right? So now my ith position is here. Ith position is here. Now what I'm doing is numt is equal to 10 into numt, 10 into 0 again, plus ti, which is 1. So 10 into 0 is 0, plus 1 is equal to 1, which is exactly what we get here. Again here, 1 into numpy, 1 into 10, plus this I is here, right? P of I int is 2, which is equal to 12, which is exactly. Okay, I'll quickly do one more. So again, this is, so each time we are multiplying by 10, right? And taking the next digit and adding it. So this is nothing but 1 into 10, which is 10, 10 plus 2. So num t is 1 into 10 plus 2, which is 12, which is exactly this. And num p is equal to 12 into 10, which is 120, plus 3, which is 120. Okay. Right. So we got these two. So this is my initial numbers, num t and num p. Then what I will do is, yeah, so, okay, is this calculation clear? Any doubts here? Yeah. Now what we are doing is we are checking if they are equal. Okay. If they are equal, then like before we append. So this is the initial case where I'm checking whether it is equal, right? If it is equal, then I know at the 0th position itself, there is a match. But in this case, we see that it is not matching. Now, since it's not matching, now what should we do? One way to think about it is shift this, right, by 1. So now actually what I want is, I want this, sorry, I want this number, right? I was on 0, 1, 2. Now I actually want 1, 2, 3, right? And another way to do that is multiply. So this can be 3 plus 2 into 10 plus 1 into 100. Right? So in that way, you're doing 3 multiplications. But instead, there is an easier way to calculate numt. Okay. There is an easier way to calculate numt, and that is what this algorithm is doing. Okay. So let me just write it again, 0, 1, 2, 3, 4, 5, 6. So numt we know is 12. Now we want to look at the next entry, which is this, right? So what we'll actually do is we will take numt, okay, and so yeah, so now where is now my I is here, okay, my I is here. Yeah. Maybe let me take some another example so that you'll understand. So imagine, let's say this was 1, 1, 2, 3. Okay, so numt will be 1, 1, 2. Okay. Yeah. Now, actually, what you want to do is transform 112 into 123. Right. So what you will actually do is take numt, which is 112. Now subtract from that, you will subtract what is t minus 1, which is this. Sorry, I minus 1, right? You go back and that is 1. Okay, this part. Okay, this part, which is nothing but 1 into 10 raised to length of p minus 1. So what is my length of p? 1, 2, 3. 3 minus 1 is 2. Okay, so which is nothing but 112 minus 110, which is equal to 12. Okay, so somehow we are able to get this part.
Minus 100. 112 minus 100. Right?
Oh, sorry. Yeah. (112 minus 100). Okay, so we got this part. Now, like the previous algorithm, like the previous step, we multiply numt. We multiply numt, which is 12. 12 multiply by 10 and add. Yeah. Remember our I is here plus length of p minus 1, which is we go till here, which is 3, which is 120 plus 3, which is 123. And we got this part. Okay, so these two steps are actually used to shift or calculate the shift by 1. Okay. There is another way of doing this, right? So we know my pattern is 3 digits, right? So what I could have done is I could have taken this, multiplied it by 100 plus 2 into 10 plus 3 into 1. Next time I could have done 2 into 100 plus 3 into 10 plus 4 into 1. But that is like each time we are multiplying it, we are doing the multiplications equal to the number of the length of the pattern, right? So let's say in this case it was just 3, but if it was 4 or 5 or whatever, right? If it was a large pattern, then we would be doing so many. So let's say the length of this was m, then each time we would be doing m multiplications, right? But in this case, each time we are just doing 2 and a multiple, yeah, 2 or a constant number of multiplications, right? Or operations. So in a way, you're just doing 2 main operations. So in that way, we can reduce the complexity in that way, right? So each time we shift by 1, and unlike a string matching algorithm, here we are actually comparing, right? We're actually comparing two integers, and if it is equal, then we append or else not. All right. Any doubts in this algorithm? Right. Yeah. And the doubt, yeah, which Kaushik raised was, see, it is especially if our in this case we got away with it because we could represent each of our alphabets, right? With 0, 1, 2, 3 up to 9, right? But there could be more than 10 alphabets. And in that case, what we can do is, yeah, we can reduce it to the base k. Right, and yeah, and it is not as straightforward as just multiplying and dividing by k. Yeah, there are some more things which are involved. Maybe I'll just take a quick example, right? So let's take a simple case of base 2, right? I think then based on that we can see. So base 2 means there are only two alphabets, 0 and 1. Let's take A, B, for example, right? So if it is if I take A, B, B, A, B, and A, B, right? So now this becomes 0, 0, 1, 1, 0, 1, and this becomes 0, 1, right? And now, like the previous case, we need to compare, yeah, each of these, right? This with this, this with this, yeah. So let's try to apply this algorithm, right? Sorry.
So, excuse me. Sir,
Yeah, yeah.
in Rabin-Karp, it is stated that we have to treat each letter as a digit. So, the string which you have taken in T, A, B, B, A, B, we will take every letters in that string as one digit, like 0, 1, 2, 3, 4, 5. And AB is a pattern. And in that now we have to check that AB is coming how many times in string T, and the position where the pattern is starting, we will take that number as an output. Like AB is coming 2 times in T at position 1 and position 4. So we will return 1 and 4 as the output,
Exactly.
right?
Yes, yes, yes.
So I'm not understanding why are you taking 0, 0, 1, 1, 0, 1. It is quite confusing.
Okay, okay. So this is a separate example from this, sir. This, you are clear with this, right?
Yes, sir.
So now I'm telling, now let's say I have, um, now let's say I have 26 alphabets, okay?
Okay, sir.
Now I need to give a number to each alphabet, right? So let's start giving. A is 1, B is 2, C is 3, D is 4, E is 5, F is 6, G is 7, H is 8, I is 9, and J should be, yeah, so you're understanding, right? So I can't give 10 because in my decimal system, I have digits only from 0 to 9, right?
Okay.
So, well, yeah, I can give this as 10. Okay, let's take the example. K is 11, J is 12. So let's say J, K, L, M is 13. But then I have to consider all of this to the base let's say, for example, 26 and not 10. Confusing?
Yes, sir. Okay. Understanding.
Yeah, but you understood the difficulty, right? We cannot,
Okay, sir.
one drawback of Rabin-Karp is we can do it. So as the number of letters increase, right, we cannot take a normal base 10 uh, numbers, right? The base will change uh, accordingly.
Okay, sir.
And this base is important because we do this num-t calculations, but to know how many digits should we shift.
Correct. Yes.
Okay,
Yes.
so the base is used for that. So instead of, in this case, we are multiplied by 10 in this current program. That means it's base 10, and therefore we have taken it as 10, is it?
Yes.
Okay.
So maybe,
Which
yeah,
means
go ahead.
if you use special characters and all that, there will be a lot of numbers to consider. Okay.
Exactly. Yeah. All right. Yeah. So I won't go to the details then. So, right. So basically, you understood the motivation, right, for uh, why Rabin-Karp for particular up to a particular digit it will work, but after that you have to change the base.
Yes, sir.
That's clear, right?
Mm.
All right. So that was, yeah, to summarize, Rabin-Karp, unlike the previous two algorithms which we saw, brute force was moving one step at a time. Uh, the second algorithm, which was this Boyer-Moore, right? That was, we were shifting things. We are moving to the right and checking backwards. Rabin-Karp does a different approach where it translates it into numbers, right? And the next one. Okay, but before that, I think you all had a doubt in the automata, right? Where is that? Okay, so I hope things are clear till now, right? Yeah. Yeah. So the motivation for automata is actually coming from Boyer-Moore, right? Where we said, let's say our string was T, A, all A's. Oops, sorry, A there. And we have a pattern which is B, A. Hmm? And what we what we realized was that, so if you take this example, yeah, this is matching, this is matching, this is matching, this is matching, but unfortunately, this is not matching, right? Now, instead of moving this to the right, is there a way in which we can, so yeah, so what does this mean? This means that, okay, what this tells me is that what we know is that this much was matching. Okay. What we know is this much was matching. right? But unfortunately, in Boyer-Moore, we are not exactly capturing this information. Like, for example, how much of my string, right, is actually getting matched by the pattern, right? That has not been, that we are not explicitly getting from the algorithm, right? And if there was a way to get that, let me just, yeah, let's take this example. So if it was A, B, A, B, A, yeah, if my pattern was A, B, A, B, A, C, so now let's go back to the previous one itself, right? We are matching from left to right. So this is matched, this is matched, this is matched, this is matched, right? So we know that this much is matched with this much already, right? And we go to the next, right? It's matching. Now this is not matching, right? But we know something, right? From this, there is some additional information which is there, which is that this part, if you notice, this is some prefix of the pattern is matching some suffix of the pattern. Right? Let me repeat that. Some prefix of the pattern, because we are moving in this direction, we are moving from left to, now remember we are moving from left to right. Okay. We were able to match up to a particular point and then it didn't match, right? So that means that some part of the pattern matched, which is the prefix, and some part of the text matched, right? Which is some part. So in a way, if you see, if up to this particular point, this is actually the suffix or the last part of the text up to that point, right? So in short, we are able to see that some part of the prefix of the pattern is matching with some part of the suffix of the text, right? And if we are able to bring both of them together, right, then, it makes our life easier. Why? Because let's take the previous example, right? A, B, A, B, A, B, A, C. If we were just doing a brute force thing, A, B, A, B, A, C, we would compare this with this, 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 and we realize, oh, B and C are not matching. These two strings are not matching. Then the next position I would take in the brute force would be start from here, right? Then I would check A, B, A, B, A, C. Right? I would have checked A, B, A, B, A, C. I would have checked this with this, this with this. But we already know that A, B, A, B, A, okay, whatever. A, B, A, yeah, A, B, A, B is actually all that much matched, right? And that information somehow we are not, that information we are not storing in the brute force method, right? So if there was a way to actually match this prefix and the suffix, then we can bring both of them together. Okay, it's not shown here. So we could align both of them together. So in this case, if we could bring A, B, A, B together, right, which is A, B, A, B, AC. And then compare, we could, in the second match, in the second run itself, we could have, or in the next run itself, we could have found a match. Right? So that is a way of intelligently trying to see what all, parts of my previous runs are matching with the pattern and somehow trying to align the pattern with the text. Okay, is that part clear?
So in this case, what we are doing is we realize that B doesn't match with C, which is the last character. So what we do is we then look for B's corresponding match in pattern, is it? So that is, we are looking at where B is matched in the pattern earlier, and then from there, how many matches do we have that we can carry forward?
In a way, yes, yeah. But we are not only remembering whether B has occurred, but before that, before
B,
whether,
A, B. Okay.
yeah,
All the
this
three.
exact pattern, has it occurred before? Yeah.
So because even though in the previous one we have matched A, B, A, B, A, which is 5 characters, but the one that doesn't match is B, and therefore we start with B and look for the. So that is the suffix. That's what you're calling as suffix. From the last 4 characters is a suffix, and we are matching it with the prefix here.
Prefix. Yeah.
Okay.
But sir, what is the benefit of keeping track of the earlier match pattern?
What is the, sorry? What is the
benefit of keeping track of the earlier match pattern?
Yeah. So this example which I gave, no? Like let's take A, B, A, C, right? So in the brute force way, if we had to, and this is the pattern which I wanted, A, B, A, C, right? Yeah. So in the brute force way, what we would have done, we would have compared A, B, A, and when we see that there is no match, we would forget whatever was matching previously, and we will just increment by 1 and now compare this with this, right?
Yeah.
Or the other case of even in the Boyer move, where we said, let's say there is A, and we have a pattern, let's say A, B. Even in B, B, A, right? So even in the Boyer board, what we are doing, checking this, and then we realize that this doesn't match, right? So if there is a way for, and remember in Boyer mode, we just looked at the last element which is matching. We did not see whether a group or a suffix or a prefix was matching, right?
But sir, here the pattern starts with B. So how, like, the AA 4A string will be prefix?
Sorry. Yeah, I did a mistake. Yeah, it's not a prefix. No. So what I'm saying is, in Boyer mode, we just considered one alphabet. We did not consider a pattern or a group of letters together.
Okay.
Or for example, let's take this itself. No, let's take A, B, A, C, and let's take my string, my pattern as A, B, A, B, A, C. Right? So let's apply Boyer-Moore to this, right? So what will by how much will it shift?
Shift
To
by
the
2.
right. It will?
Shift by 2.
Okay, why by 2?
Because we will match the last character B with C,
Hmm.
and it is not matched here. So we'll compare.
Right.
So we have a B,
Which is here, right?
yeah. So we'll shift it by 2.
Right. So we will shift this by 2 and so this will be A, B, A, B, A, C. Right? And we see that it is matching. Right? Yeah, and here somehow luckily we so the point to make is here we are just looking at where B is with B, right, in the pattern. We are not actually checking whether, what if there is a group of letters which are occurring together.
So what is the benefit of checking that?
Yeah, that's a good question. So what is the benefit of checking that? No? So let's take this example itself. No? 1, 2, 3, 4, 5, 6, and
Sir, in case Boyer-Moore, after shifting the B to the B, again for checking the matching entire pattern as well as entire text subsequent character will be matched. But in case of this case, so the already matched character will not be checked. The remaining subsequent AC will be matched, and once it is the entire match is happened, then only it will be treated as a both the strings are matching. So we are getting a benefit of 4 characters calculation, maybe that we are saving.
Yeah. Sorry, I forgot that. Yeah, thanks, Tushar. So that's a good important point. So even in this case, if you see, even though we aligned B and B together, right? Still we have to do we have to match all the we have to start from here and go all the way back.
Character by character.
Sorry,
We have to go by character, right?
character by character, right. But if we
Group them together.
if this is already matched, right, then we have to just check for the remaining letters, right, to the right of it.
Okay.
So in a way, Boyer-Moore remembers just one character match, whereas this remembers a complete set.
Exactly. Yeah.
So in this case, where B is not matching with the C, then you are going back and finding which are the characters is already matched. So then we found that AB is matching. And suppose in this case, in the text for AB, the last B, suppose it would have been something else, maybe E, D, or something else. So in that case, the previous matched character will be ABA in the text and ABA in the pattern. So this actually how it is being recorded. That is again my doubt. So
Yeah, we'll come to that. Yeah. right? So, good. So we know like what is the difference between this and Boyer-Moore, right? In if in the automata, what we're going to look at, and the KMP algorithms, if what they're trying to do is somehow trying to capture these groups of prefixes and suffixes so that we need not revisit them again, but we can just look at the right. So that is what, yeah. So one way to do that is by looking at this automate, right? So yeah, well, what we actually do. So this looks very confusing, but it's very easy actually. So let's say my pattern P, right? I think in this case it is, what is my pattern? Yeah. So actually this automata or this graph is actually helping us remember the that pattern or that suffix. Okay. Or what does it say, right? So this is a graph which has nodes moving, there are transitions across nodes, right? So our pattern is, let's say, A, B, A, B, A, C. This is my pattern. Okay. Now, what this is saying is that, okay, now let me take a text also with it. A, B, A, B, A, B. A, B, C, A, B, A, B, A, B, A.
AC and AB, I think.
Yeah. Right? Okay. AC, yeah. Okay. So I'll come to how we got this, but let's say we have this at our disposal, right? We have this kind of graph structure which is there, which will actually help us remember what we have seen in the past, right? So in a way, this is like a the basic memory unit, in a way you can say, right? So each of these nodes, or these are known as states. So 0 refers to some state, and have a separate meaning, so as to say, right? So if you think of it, 0 tells me that I have seen only bees. Okay. State 1 tells me that I have seen bees, then, or I may not have seen any bees, but I've seen one A, one or multiple A's. Okay. Similarly, state 2 tells me I have seen B's followed by A's followed by B's, or I have just seen A and B. Okay. So let's say this, we have this at our disposal, and with this, we will try to determine what are the prefixes which we have already seen. Okay. So we will, this text will be an input to this automata. Okay, this text will be an input to this automata or this graph, right? So we read A. Okay, so A tells me, okay, I was at 0. I move to 1. Okay. The next is B. B tells me, okay, I was in 1. Now I move to 2. Now I come here. Now at 2, when I move, I see A, I move to 3. Move to 3. Okay. And 3, when I see B, okay, move to 4. A, go to 5. All right. Now at 5, when I see a B, what should I do? Go to 4. Okay. Now at 4, now when I see an A, again go to 5. Sorry, where am I? Here, right? Hope I'm correct. Yeah. Now at 5, when I see a B, when I see a C, go to 6. And whenever I reach 6, I can say that there is a match. Okay, and what I do is and we can see, right, that match is here, A, B, A, C. This match is happening over here. So what this automaton is doing is it is kind of, and if you look at the numbers, right, this tells me that how much of my prefix, how much of my pattern is already matching in the text. Okay, let's look at that. How much of my pattern is already matching in the, how much of my pattern is matching in the text. So initially, we see that nothing is matching. We have not started reading the text at all, right? Now we yeah. So yeah, am I audible? Hello?
Yes, sir.
Okay, so yeah. So now we come here, we have read an A. And what that means is, and because of reading that A, we have moved to state 1, which is this. And what does that tell me? That tells me that in my pattern, I have something, okay, I have a prefix, or in my text, there is, and my pattern, there is one character which is matching, or one prefix, or prefix of length 1 is matching. Okay, then remember from A, when I saw B, I went to 2. So when I went to 2, so what does this tell me? Look at this pattern, AB. AB is telling, and you can see that AB is also there in my pattern. So what it is telling is that there is a prefix of length 2, which is being, up to this point, there we can see a prefix of length 2, which is matching in the text. Now when I went to A again, so I moved from 2 to 3. So this is my pattern, ABA. And you can see that, yes, there is a prefix of length 3, which is there in my pattern, which is matched by my text. Then from A to B, I go again, and I see that I go to 4. Okay, so AB, AB is matched, right? Now from 4, again I see an A. I move to 5, right? Now is the interesting part, right? Now I actually see a B. Okay. So when I see a B, notice that it is telling me to go to state 4, right? So now what it is telling me is that now you have actually seen a B, and that means now I have a prefix of length 4, which is this. Okay, if you see, that matches with this.
I think there are 2 more steps that were missed. So
Yes, sir. You have skipped 2 steps.
Sorry, which one?
So I think it'll go to 4, 5, 4, 5 a couple of times before it goes to 6. I think that middle part was missed out.
Oh, sorry. Oh, I missed that, huh?
Yeah.
A, B, A, B, A, B. Oh, again, there's a 4 and a 5, right? Sorry, I missed. Yeah. Right, and then from 4, when I see an A, it tells me that it moves me to 5, and this is the pattern which I get, right? And then finally I move from 5, when I see a C, I move to 6, and I get this pattern here.
Sir, from 5, as it is B, we are returning back to the 4. And instead of B, if it would have been A, probably from this graph, it should return back to the 1.
Yes.
So whereas we already matched AB, A, I mean 4 already we matched. So why it is returning back to 1?
Yeah, that's a good question. Let's look at it a little more carefully. Let's take a simpler example. AB, AB, A, AB, AB, AC. So let's take A, B, A, B, A, A. A, B, A, B, A, A, A. Then let me take B, C, something. Okay. So we are at A. Initially we are at 0. Okay, let me write this. We are at 0. When we see A, we move to 1, right? And what does that mean? I have something. I have a prefix of length 1. When I move from A1, I move to 2. I have a prefix of length 2. From there, I move to 3. I have a prefix of length 3. Right? This and this are matching. Then from 3, I move to 4. On seeing B, I have this. Now, from here, I move to from 4, when I see an A, I move to 5, right? I have a prefix of length 5. So far, so good. Now, from 5, when I see an A, I go back to 1. Okay. So what does that tell me? Now, actually, my prefix, right, which matches my text is only of length 1, which is this. And let's look at the text. Isn't that true? Because whatever we had almost matched till here, but because this A came in between, A, B, A, B, A, And since an A came, it broke the entire pattern, if you notice. Right? Now we have to go back all the way back here, and we have to start checking from here. Tushar, you understood that?
Yeah, I understood. Actually, following this graph is clear. Now, making this graph, how it is being made, that part of code I need to understand.
Yeah, sure. Okay. Yeah. So, as so that is the important part, right? So, how do we actually construct this automata, and how do we actually translate this into code? Yeah, that is the KMP algorithm, right? And we'll look at that now. Yeah, we're running short of time, but we'll do that. Yeah, any doubts still here?
So just one question, sir. If it is, for example, ABCD, pattern is ABCD, and the text is ABCB,
Pattern is
then
ABCD.
ABCD, and the text is, let's say, ABCBEF or something, ABCBEF.
Yeah.
No, ABCB, B for boy.
Okay.
So in this case, when we get to B, what you're saying is we'll go back to 2, is it? So it'll be 0 to 1, 1 to 2, 2 to 3, and from 3 we'll go back to 2. That's what meaning is it? Or
go back to 0.
No.
Go back to 0. Okay.
Yeah, go back to 0 because why? What does it tell me? It tells me that all that it is telling me is till now, what prefix of P have I seen or can I take forward, right? Because when I encounter a B, right, you will see that we will look at all the suffixes, right? What are the suffixes till now? ABCB, BCB, CB. We see that none of them match with the pattern.
Right.
So we have to go all the way back to 0.
Okay, so that 0 is not just an automatic understanding that if I'm looking at B, therefore just 0, but there is a computation involved, and that's what KMP does, is it?
Yes,
okay.
yes. Yeah.
Okay. Thank you.
All right. Yeah. So KMP.
That is the tough part, translating all this into code.
Yeah, but I saw someone posting a very good video on Discourse, which explains this KMP very well. So I would encourage all of you to go to Discourse. I think the topic is automata. Yeah.
Yes, sir. I too watched the video. That was a really good explanation.
Yeah. I also found that video was very nice. So I would encourage all of you to go and look at that video. That explains the Knuth-Morris-Pratt algorithm very well. Okay. So yeah, thanks, Viraj. Thanks for posting. Yeah. So So what actually the Knuth-Morris-Pratt algorithm does is to somehow, so let's say this is my so this is my text and this is my pattern. It somehow tries to get the suffix of the text which matches the prefix of the pattern, such that we can bring both of this together, right? And then we need not compare all of this because we know this is already equal. We know this matches this matches this. We know all that. Then we can directly start checking this with this, right? So that is what Knuth-Morris-Pratt algorithm does. Somehow try to calculate the suffix and the prefix, right? So let's just look at this. Yeah, maybe I'll explain the algorithm first. All right. Okay, so let's take that same example of we have a oops. Okay, so we have A B A B A B A B A C A B. This is my text, let's say, and my pattern is A B A B A C. Okay. Now, what I actually want to do is, yeah, I follow, right? I check this with this, it's matching. I go ahead, this with this matching, this with this matching, this with this matching, this with this matching. And now I realize this is not matching this, right? Now, what I want to do is look for a prefix here which matches the largest prefix here which matches the suffix over here, right? Whichever it can be, right? So in this case, it's easy to realize, notice that, right? What is that which matches the longest suffix here? AB, AB, A matches AB, AB, A. So what I actually need to do is shift this. Oops, sorry. Yeah, let's see if this works. So what I need to do is shift this
Only AB matches, right?
sorry.
Only AB matches, right? Not AB.
Sorry. Let's take the, yeah. So it is, yeah. So you look at all the prefixes of P, right? Which is, so which all are the prefixes of P? There is AB, ABA. Then there is AB, AB, right? Then there is ABA, ABA, all of that. Now we look at all of the prefixes here in the pattern, and we check which of them match or correspond to the suffix over here, right? So which does it match?
So which part?
Yeah. So we came till here and now we realize that these two are not matching. So then we look at the suffix here, sorry, the prefix here, which matches the suffix here.
So the ABAB will match. ABAB prefix will match.
AB,
AB.
AB, AB. No. So AB, okay, let me just see. AB is the prefix you're saying. And how is it matching? Which suffix is it matching?
Uh, like after leaving the first AB, the next two ABs it is matching.
This you're saying?
Yeah.
No, but we haven't reached here, right?
So first of all, yeah, we are considering only the first 5 letters you're saying, right?
Correct. Yes. Yeah.
So
So we yeah.
then it will
Yeah,
match
go
the
ahead.
complete suffix, like the complete word is the suffix itself. AB, ABA.
AB.
A.
No, AB. Sorry. Yeah. Okay. So in that case, what will happen? Wait, I think I've made a mistake. No, I think it should only match. One. So yeah, so we have AB, and yeah, AB, AC, and we realize that this is not matching. So then we look at the suffixes of
So sir,
yeah.
if we are
Yeah.
comparing this B and C, then we can say that ABAB is matched till this point. This is the
Yeah.
maximum suffix that will be matched with the prefix from the pattern.
Yeah. So the maximum, so that will be AB, right?
Yeah.
Yeah. Sorry.
In the
Yeah.
first occurrence, we'll match the ABA suffix, and in the next like move, if we compare B with C, it is not matching. The maximum suffix that match is ABAB.
Which is this, right?
Yeah.
Sorry. So we have to include this also. Is that what the algorithm is saying? Wait, let me just check again. We are checking. We are going from, yeah, if it is not matching, what do we do?
So we'll move to the Elif part.
Sorry?
We'll go to the Elif condition because it is not matched. So we'll move to the Elif condition.
Right. Yeah. So we'll move to that, and we will go to, we'll find a smaller prefix. So when we look at a smaller prefix, what is it? It will be AB, right?
Yeah.
And so we will shift this to AB, AC. This part, right?
Yes, sir. Again, we'll compare A with A. Now it is matched. So the suffix will be AB.
Right. Okay. And then
And
we look at B and C,
so
and
again, the suffix will be AB only.
again the suffix. So we have to include this also, right? I think that's the mistake I made,
Yeah.
right?
Yes, sir.
Okay, sorry about that. I missed that. Okay, sorry for the confusion. Let me explain it again. So let's say our text is AB, 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 AC, AB, and my pattern is AB, AB, AC, right? I go on till I don't see a match. So in that case, it is this, B and C are not matching. So then, so what that tells me is that I want to look for suffixes including B, right? Because B is not matching with this, which is a prefix in P. So I will see that AB is the longest such prefix, right? So I
Yes,
will,
sir.
Can you please repeat? I mean, why it is not A?
Yeah, in the first move, it will be AB, because before reaching the B part, like before comparing B and C, we'll reach up to A. So the first suffix will be AB. Then in the next check, when we will check B and C, we'll update our suffix with AB only, because that is the maximum suffix we are getting from here.
Why it is happening in the code, sir? Please, can you
okay, let's
side by side?
okay, let's look at the code. Yeah, but before that, I just wanted you all to get an intuitive idea of what is happening. So, there are, so first condition, check here. This is the easiest part, right? When I oops, sorry. Yeah, when I check A with A, it's matching. B with B is matching. A with A matching. B with B matching. A with A matching. I'm going ahead. When I see that there is a mismatch, right? I stop there and I look at all suffixes, okay, and all prefixes of P, right? So what are the prefixes of P? AB, ABA, ABAB, ABA, AB, and A. I check which of these correspond to suffixes in T, the longest such one, right? So which are the suffixes of T? There is B, AB, BAB, ABAB, BA, BAB of length 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? And which is the longest among, I mean, which is the one which is matching and the longest? ABAB, which is ABAB, which is ABAB. So then I move this, right? right? Is this clear?
Yes, sir.
No, sir. The suffix in T includes AB, AB, A. And in this case, you are tracking from right to left. So BA, BA, and BA. And then you are matching which are the character in the pattern in the prefix is matching, and you are identifying AB, AB. And same is for both text and the pattern.
Right, right.
I mean, why not tracking it from left side? So it would have been the matching both suffix and prefix AB, AB, A.
No, no, we haven't reached this. You're saying A, B, A, B, A. Are you talking about this?
Yeah, both the cases. I mean, for see in pattern, we are where it is not matching, B in the text and C in the pattern is not matching.
Correct,
So
correct.
till now, what we have seen what are the matched character AB, AB, A in prefix in pattern and AB, AB, A in the text.
Right, right,
So from
right.
here, we are now concluding that the maximum matched character in both T and P is AB, AB. How we are coming to this conclusion? That I'm not
Because
a bit
we
clear.
have to include this B also, right?
B
Ear-
in text.
B
Earlier,
in the
yeah,
text.
yeah,
Yeah.
B in the text. Earlier, we were only considering the A, B, A, B, A. Now we are comparing this B with C. So we have to include this B also in the suffix.
That's correct.
So that is why now, like, now if we see that what is the longest match for this suffix, so that will be AB, AB, right?
Including B, the last
Including
B.
B. Yeah.
Yes.
So that is what the algorithm is doing.
Okay.
Yeah. I hope it's clear to you now.
Yeah. Now, yeah, sir, continue.
Okay. Okay. All right. So now then we match again this A with A, and we see that it is matching. So we increase the prefix and the suffix, right? Now again we see that this and this are not matching. So we yeah, now what we again try to see. So now this is my prefix till now, right? A B A B A. Now I look at the suffixes of my text and the prefixes in my pattern and see which is the longest one which is matching. So in this case, what are the suffixes of T? It is B is there, AB is there, BAB is there, AB is there, BAB is there. What are the
Sir,
prefixes of
one doubt, sir. Why are you not taking the complete word as a suffix?
of T?
Yeah, of T and of like the complete word can also be the suffix and prefix. Like
If
it
the
can be
complete word
matched,
is
right?
taken, it will be fully matched. No,
Yeah,
but because the last character is not matching, if we can't, for sure,
so
the suffix has to be one letter less.
that is what the algorithm is doing now. Like we started from a single letter, so we are considering that single letter as the suffix, right?
Right.
So we have to
Yeah.
take the complete word also, the suffix, and in the pattern also we have to take the complete pattern as a prefix.
Oh, so we have to, yeah. So we have to take AC as the prefix you're saying.
Yeah, in the cases we have to take like in the suffixes here you are writing only ba bab. ab should be there also.
2, 3, 4, 5, 6. So my pattern 1, 2, 3, 4, 5. Yeah. Sorry. Yeah. AB. Right?
Yes, sir.
Yeah.
That will never get used though, isn't it? Because
But algorithm, like we are using our algorithm, so it should compute this thing also, right?
okay.
Yeah. Good point, Viraj. Yeah. So then again, I look at all the prefixes, right? Which is C, AC, BAC, ABAC, BABAC, and ABA. Yeah, that is there, right? So now, which is the suffix? Which is the longest such one?
Prefix will not include
Sir,
C, isn't it, sir? Because C is not matching correct.
you are writing the suffixes of P. We have to write prefix actually.
Sorry.
Sir, you have wrote the suffix part. We have to write the prefix.
Sorry about it. Sorry. Yeah. So it is A B A B A A B A B A B A A B and A, right? Now
Also,
again we look.
AB will also be the complete pattern.
Yeah, correct. A B C, right?
Yeah.
And now again we see that AB and AB are the longest such ones, right? So then we move such that AB matches, right? And then again we extend and we extend and we get the match. Right?
Yes, sir.
Okay, so now let's look at the code. Let's look at the code. Now notice that in the code there are two parts, right? One is somehow by inspection we could realize, by how much to shift, right? But we need to write an algorithm for that also. So A, B. So let's take the pattern, right? A, B, A, B, A, C. Now what the algorithm does, okay, let's take the pattern. P is A, B, A, B, A, C. Yeah. So what the algorithm does is it creates this list, right, called the fail, which tells me that at a particular point, if there isn't a match, by how much should I, or what is the prefix which I should look at, right? So for example, in this case, I have initially all are initialized to 0, right? So this is 0, 1, 2, 3, 4, 5, and okay, 0, 1, 2, 3, 4, 5. All are initialized to zeros, right? And what this is actually doing is it is somehow we are matching the pattern with itself. Okay, so we take A B A C, right? And we create another copy of the same pattern and we consider that as the text. Okay, and yeah, so let's take this as the text. Okay, in this case, right? But both are actually the pattern. And we want to somehow compute this fail matrix, fail list, right? That's what we want to do. So what we do is we take J as 1, right? In this case, let this be J and K is 0. So we take K here. Now our J goes till M, right? Now what we do, we will check if this matches this. P of J is equal to P of K. Is it true or false in this case?
False.
False, right? So, and is K greater than 0?
No.
No, right? I'll come to the reason why we are checking that. And then, so that is also false. So then J is equal to J plus 1. We just proceed ahead, right? J is here. Okay. Now we compare P of J with P of K, which is this is compared with this. Yes, there's a match. Okay. So like our previous example, whenever there is a match, right, we increment both J and K, we go by 1. And what does this tell? Okay. So what this tells me is that there somewhere, there is a prefix, right, whose length is whatever this K plus 1 is, right? So fail of J remember is this, right, which is 0, 1, 2. Now, so whatever is my letter at 2, right, I can find a prefix of length K plus 1, whatever K plus 1 is. So in this case, it is 0 plus 1, which is 1. So now my fail becomes, this is fail of 0, 1, 2. 2 becomes equal to 1. Okay, now I increment J, I increment K. Okay, now again J and K match, right? So what does that tell me? That tells me that somewhere behind I have a, so fail of J, which is this one, 3 is equal to K. Remember my K, what was it? Okay, K was 1, right? So I have found a prefix of length 1. That's what K tells me. Now I will increment K by 1 and put that in fail of J, which is here, right? And I increment K and J. Then I look at P of J and P of J and P of K. And what do I see? Again, there is a match. Fail of J, which is fail of 4, is equal to K plus 1, which is 3. K is equal to 3. Hey, hello. Sorry, somehow my system just crashed. I just restarted it again. Let's do one thing. I will tomorrow Atul will be taking the session. I'll just tell him to go through the KMP algorithm. Is that okay?
Okay, sir.
Yeah, sorry about that. I don't know, my system just crashed. Yeah, I'll inform. Yeah, sorry about that. Okay, see you all. Chalo, bye.
Okay, thank you, sir.